For decades, we treated Pluto like the solar system's frozen basement, a dull cue ball drifting in the dark, far from the sun's warmth. Then, in 2015, one flyby from the New Horizons spacecraft completely rewrote the textbook overnight. Instead of ancient, crater-pocked surfaces, we saw smooth, surprisingly youthful plains. Instead of silence and stagnation, we found compelling signs of an internal engine still humming. And get this. That engine isn't just running. It's powered by radioactive fire, buried deep beneath a crust of water ice, nitrogen snow, and ammonia-laced water that absolutely refuses to freeze. This little dwarf planet, it turns out, has a complex, differentiated internal structure with a rocky core wrapped in a thick mantle of water ice, hinting at far more going on than we ever imagined. Picture the coldest place you can possibly imagine. Pluto, a staggering 40 times farther from the sun than Earth, where sunlit noon is dimmer than twilight on a moonlit night here on our home planet. Now, imagine a world in that extreme cold where glaciers flow like thick molasses. Icebergs the size of Manhattan drift across vast nitrogen seas, and a hidden global ocean sloshes against a rocky core, kept perfectly liquid by heat, slowly bleeding out of radioactive rocks. Not quite the dead, inert ice ball you were promised, is it? The first crack in the story. When New Horizons snapped its closest pictures, the biggest, jaw-dropping surprise was Pluto's heart-shaped feature. Sputnik Planitia, a colossal basin wider than Texas, was shockingly flawless. Virtually no craters, no scars, as if someone had hit the reset button on its surface just yesterday. On geologic timescales, though, yesterday means something like 100 million years, which, for a planet, is practically this morning. A crater-free surface demands a powerful resurfacing agent, something that constantly erases the cosmic record of impacts. On Pluto, that agent is nitrogen ice. But here's the kicker. Nitrogen can't glide and churn with such vigor unless something is warming it from below. The absence of craters, combined with evidence of extensional tectonic faults, was our undeniable first hint. Pluto has a heater, and that heater is most definitely still on. Scientists even hypothesize that Sputnik Planitia itself might have formed from an impact, only to be subsequently filled or uplifted by buoyant material from that subsurface ocean. The lava lamp on the edge of the solar system zoom in even closer on Sputnik Planitia, and you'll see the nitrogen plane isn't static at all. It's divided into distinct polygonal cells, each about 20 kilometers across, slowly turning over like a mesmerizing cosmic lava lamp. Warm ice rises in the center of these cells, cools at the surface, then gracefully sinks at the edges, a process we call convection. These gentle, continuous overturns effectively wipe away impact scars the way a baker smoothly frosts a cake. But, as you might guess, convection needs energy. On Earth, our planet's mantle rock stays plastic thanks to leftover primordial heat and ongoing radioactive decay. On Pluto, the very same physics applies, only the working material is primarily nitrogen ice, along with methane and carbon monoxide ices, all at an astonishing minus 230 degrees Celsius. For these volatile ices to stay soft enough to convect, the base of the glacier needs to stay just a few degrees warmer than the top. A subtle but crucial difference that can only be driven by heat oozing out of the dwarf planet's deep interior. Mountains of ice that shouldn't be there. Rising majestically along the western rim of Sputnik Planitia are the Aladrisi Mountains, water ice peaks as tall as the Rockies. Water ice at Pluto's frigid temperatures is incredibly hard, as unyielding as bedrock. It can easily hold up kilometer-high cliffs without crumbling. Yet these same peaks are remarkably jagged and youthful, not rounded and eroded by eons of sublimation, as you'd expect on a truly dead world. Youthful mountains like these demand uplift, perhaps even active cryovolcanic resurfacing. The only plausible way to build and continually refresh such topography is to have material actively pushing up from underneath. This again points unequivocally to an internal source of heat, driving geological processes and even creating icebergs of water ice that float in softer nitrogen plains. The ammonia connection. Here's where chemistry truly joins the conversation and offers another critical piece of the puzzle. Ammonia, when mixed with water, forms a brine that can remain liquid down to an incredibly low -97 degrees Celsius. Spectral fingerprints from Earth-based telescopes and New Horizons data clearly show ammonia in patches, particularly around fracture zones on Pluto's surface. Ammonia-rich slush is naturally buoyant. It can rise through cracks and fissures, effectively burping onto the surface, painting the landscape with fresh new ice and other materials. The presence of ammonia in erupted material isn't just interesting, it's a smoking gun. Strong evidence that a subsurface reservoir exists and is actively communicating with the surface, keeping that hidden ocean from freezing solid. The ocean. Beneath the ice. Now let's put all these compelling clues together. The curious lack of global contraction belts on Pluto's surface, the widespread extensional faults indicating expansion, the mobile, convecting nitrogen glaciers, those rejuvenated, youthful mountains, and the unmistakable ammonia signatures. When planetary modelers feed all this data into their simulations, they converge on one astonishing conclusion. Pluto hides a vast global layer of liquid water. This subsurface ocean is estimated to be a remarkable 40 to 180 kilometers thick, sandwiched perfectly between Pluto's rocky core, which is about 1,700 kilometers in diameter, and its thick, frozen outer shell of water ice. This isn't pure water though, it's probably dirty water seasoned with a few percent ammonia, and likely some antifreeze salts. It's pitch black, of course, under pressures comparable to the crushing depths at the bottom of Earth's Marianas Trench. But here's the mind-blowing part. It is liquid, and all evidence suggests it has remained liquid for billions of years. What keeps the stove burning? You might wonder how this is even possible so far from the sun. Well, the sun's warmth is far too weak at Pluto's distance to maintain a liquid ocean. And while its large moon Charon does exert some gravitational pull, tidal heating from Charon is actually quite modest. Charon's orbit is almost perfectly circular and tidally locked, so flexing in Pluto's interior is minimal. So what's the secret? Instead, Pluto's inner fire comes from good old-fashioned radioactivity. Elements like potassium-40, thorium-232, and uranium-238, trapped within Pluto's rocky core since its formation, slowly undergo radioactive decay. As they split, they release alpha and beta particles, which generate heat in the surrounding silicates. This gentle heat trickles outward at roughly the wattage of a few hundred household light bulbs per square kilometer, which might sound pathetic by Earth standards, but it's more than enough to keep an ammonia-rich ocean from freezing. Over 4 billion years, that persistent, gentle warmth has sustained a water world where absolutely none was expected. Leakage at the poles. Occasionally, this hidden ocean doesn't just push up mountains, it punches through to the surface. Take Wright Mons and Picard Mons, for example. Two giant domes, each about 100 kilometers across, that look suspiciously like Earth's shield volcanoes, only they ooze icy slurry instead of molten lava. Cryovolcanism on Pluto is subtle, to be sure. Eruptions are probably more like thick toothpaste slowly squeezing through cracks than dramatic fiery fountains. Still, each eruption brings ammonia, water, and quite possibly complex organics to the surface, painting bright splashes visible to New Horizons cameras. These icy eruptions are a direct and dramatic hint that Pluto's internal chemistry can indeed talk to its exterior, acting as direct outlets for those subsurface liquids or slushy ice. A sky that snows backwards. Even Pluto's thin nitrogen atmosphere cycles seasonally, directly linked to this internal engine. When Pluto nears the Sun in its eccentric orbit, the volatile ices, primarily nitrogen, methane, and carbon monoxide, on its surface sublimate, creating a tenuous temporary envelope. As it recedes from the Sun, this atmosphere largely refreezes, forming a delicate layer of nitrogen snow. But here's the interesting part. The snow doesn't land uniformly. Heat rising from below, driven by that internal engine, can actually guide where it settles, directly linking Pluto's climate to its internal processes. In essence, Pluto's atmosphere, its surface ices, including those reddish tholins that give it its distinctive coloration, and its buried ocean are all part of one giant, interconnected, heat-linked system. Implications for life. So, what does all this mean for the big question? Liquid water, ammonia acting as an antifreeze, organic rich surface gunk, and a stable, long-lived heat source check several crucial boxes on the habitability ledger. Of course, no sunlight means photosynthesis is impossible, ruling out plant-like life. But chemosynthetic microbes on Earth thrive under remarkably similar conditions, kilometers beneath the seafloor, powered by chemical reactions rather than sunlight. Pluto's ocean is probably too nutrient-poor and far too deeply buried for anything as complex as fish or larger organisms. However, simple microbial chemistry, powered by that steady radioactive decay, is absolutely not ruled out. If life can arise and persist in such a dark, cold, ammonia-laced aquarium, then dwarf planets across our galaxy, and beyond, could be quiet, unassuming biological oases waiting to be discovered. Why this changes everything. Before New Horizons, planetary scientists largely believed that small worlds like Pluto, lacking the gravitational heft of larger planets, would cool off quickly after formation and remain geologically dead. Pluto profoundly disproved that assumption. It proves that even bodies significantly smaller than Earth's moon can hoard enough radioactive kindling in their rocky cores to keep a global ocean alive for giga-years, billions of years. That single stunning insight catapults places like Eris, Makemake, and even the mysterious rogue planets wandering interstellar space into the realm of potentially habitable worlds. The universe's habitable real estate just expanded by billions of frozen spheres, and Pluto's differentiated internal structure and long-lived subsurface ocean are the key to this paradigm shift. If you enjoyed peeling back Pluto's complex layers and discovering its hidden depths, please hit that subscribe button. More deep space mysteries drop every single week. Share this video with anyone who still calls Pluto a boring snowball, and drop a comment telling us which dwarf planet we should investigate next. We arrived at Pluto expecting to find a fossil, a relic of the early solar system, and left with overwhelming evidence of a living, breathing world. Beneath Pluto's iconic heart-shaped glacier, radioactive embers gently warm an ammonia-laced sea, powering ice mountains, creating nitrogen lava lamps, and perhaps even sustaining the faintest heartbeat of microbial chemistry. The edge of the solar system is no longer a cold dead end. It's a powerful reminder that nature can hide engines and life in the unlikeliest of places. Pluto's internal engine is still running, and it's running on time measured in eons, quietly reshaping our very definition of what it means to be alive out there in the dark.